This is a weekly summary of interesting news that is relevant for my lectures at the Eastern Switzerland University of Applied Sciences. My name is Thomas Bocek, and today we will discuss 6 topics. The first one, it's big news. It's AWS. It's the following article here. AWS experienced a major outage in its US East 1 region that lasted for about 15 hours. The root cause was a race condition in DynamoDB's automated DNS management system. DynamoDB manages hundreds of thousands of DNS records for its load balancers. The DNS management system has 2 independent components: a DNS planner that monitors load balancer health and creates DNS plans, and a DNS enactor that applies these plans to Route 53. For reliability, 3 DNS enactors run independently across different availability zones. And here is actually the following summary, which explains quite well what happened. And what happened is that the race condition occurred when DNS enactor 1 began applying an old plan, but experienced unusual delays requiring retries. Meanwhile, the DNS planner continued producing newer plans at high frequency. DNS enactor 2 quickly applied the latest plan and triggered cleanup to delete old plans. DNS enactor 1, still processing slowly, finally applied its outdated plan to the original DynamoDB endpoint, overwriting the newer plan. DNS enactor 2 then detected this old plan and deleted it, removing all IP addresses for the original endpoint, and this left DynamoDB's DNS records empty. When applications tried to resolve the DynamoDB endpoint, DNS returned no IP address, making the service unreachable even though the servers themselves were functioning. And this cascaded across 113 AWS services, including EC2, Lambda, and SQS. The EC2 Droplet Flow Manager, which maintains lease for physical servers hosting EC2 instances, depend on DynamoDB. And when DNS failed, the Droplet Workflow Manager could not establish new leases for instance state changes. After DynamoDB recovered, the Droplet Workflow Manager tried to reestablish lease across the entire EC2 fleet simultaneously, and the massive scale meant leases began timing out before completion, causing the system to enter congestive collapse, requiring manual intervention. The Network Manager, an EC2 subsystem that handles network configuration, then began propagating a huge backlog of delayed network configurations, causing newly launched EC2 instances to experience network configuration delays. And this created additional cascading failures even after this root DNS issue was fixed. And a good overview, what happened is the following article here. The outage affected over 1,000 platforms globally, including Snapchat, Reddit, Fortnite, Slack, banking apps, and airline systems. Docker services were also affected because Docker Hub and related systems run on AWS infrastructure. So here we also saw an incident. And Docker also reported this issue around midnight and resolved them by mid-morning once AWS restored services. And I also had issues to run my Docker files, but luckily GitHub and other providers also host Docker images, and I could switch to those. So what are the lessons learned? Also here from the register, a very good article. From a distributed systems perspective, this shows several important failure patterns. First, the race condition demonstrates timing dependencies in concurrent systems. The system was designed for eventual consistency, assuming DNS enactors would only use the recent plans, but the unusual delay violated those assumptions. Second, the cascading failures showed tight coupling between services. Third, recovery became a separate problem because systems designed for normal operations broke when restarting simultaneously at scale. AWS has disabled the DynamoDB DNS planner and DNS enactor automation worldwide until safeguards can prevent the race condition from reoccurring. But this is already the third major US East 1 outage since 2020, and the concentration of internet services on a small number of cloud providers create a systematic risk when these providers fail. Then the next article, it's for my students, because during the challenge task exercise, we figured out that MetaMask has a new version. So this is to connect to Ethereum and other chains via the browser. I'm still using the old one, and these updates focus on multi-chain account support, particularly adding Bitcoin and Solana functionality along Ethereum. And the major addition includes multi-chain account with BIP44 support and Solana integration. Users can now manage Bitcoin, Solana, and Ethereum addresses on a single wallet interface. The wallet also added privacy mode for hiding account balances and support for additional networks. And the updates also restructured account management with new multi-chain account groups, changed network naming to shorter forms, and added account syncing from across devices. And for developers, in my opinion, the user experience has gotten worse. The polyethers now still show up, but if you're in dark mode, it's gray on black ground with a tiny font. Luckily, my extension did not auto-update. So if I look at MetaMask, I still see here my account on top, big letters. So this is quite nice. Otherwise, it would be somewhere down here and not as visible as before. The next article, it's about Idealist. It's the following article here. This is the world's largest non-profit job board with millions of monthly visitors, and they replaced a $3,000 per month Heroku bill with a $55 per month server using the Disco deployment tool. It's also kind of ad for Disco. This is this website here. And the cost problem stemmed from Heroku's pricing model. Each staging environment required separate web dynos, worker dynos, and database add-ons, costing approximately $500 per month per environment. With just 2 permanent environments, the team faced $1,000 monthly costs before adding any additional testing environments. And the costs scaled linearly with each environment, regardless of actually resource usage. And the team rented a Hetzner server at $55 per month and used, as I mentioned, Disco to maintain their Git push to deploy workflow. All staging environments shared a single Postgres instance running directly on the server instead of using separate managed database add-ons. The team expanded to 6 full staging environments on a single machine. 6 environments at $500 each on Heroku would have cost $3,000 monthly, and on the shared server on Hetzner, resource utilization remained low at around 2% CPU and 14 gigabytes of memory used out of 32 gigabytes. Hetzner's limited US presence was acceptable for staging, but would be consideration for production workloads serving US users. And the bigger impact was organizational. Staging environments shifted from scarce, expensive resource requiring approval to abundant disposable commodities. Developers could spin up environments for pull requests without permission or cost concerns. The real cost of this platform as a service was not just money, but hesitation and workflow friction. And as an example, for microservices, when you use, for example, the DigitalOcean app platform, each service requires its own container instance starting at $5 per month. With 10 microservices, you pay a minimum of $50 monthly just for compute before adding databases or load balancers. On a shared infrastructure, all 10 services could run on a single server for a fraction of the cost. The next article is about CRDTs, about conflict-free replicated data types. Those are data types, data structures designed for distributed systems that allow nodes to update independently without coordination while guaranteeing eventual convergence at the same state. Traditional distributed systems use coordination to maintain consistency. When two nodes receive conflicting updates, they must communicate and agree on a single outcome before responding to clients. CRDTs eliminate these coordination requirements through deterministic conflict resolution algorithm embedded in the data structures itself. The example here, it's a G counter, demonstrates how this works. Each replica maintains a vector of counters with one slot per node. When node 1 receives a like, it increments only its own slot. During synchronization, nodes merge by taking the element-wise maximum of their vectors, and this merge operation is commutative, associative, and idempotent, guaranteeing convergence regardless of sync order or timing. Now, if you want to not only increase but also decrease, you have a positive negative count, the PN counter, and this extends by combining two G counters, one for increasing and one for decreasing, enabling both likes and dislikes. And the final value is the sum of all increases minus all the decreases across all nodes. So who uses CRDTs? Notion, for example, uses CRDTs for offline collaboration, implementing one of the largest production CRDT systems, and they went live in August 2025 with their latest offline collaboration feature. CRDT differs from operational transformation, for example, used by Google Docs. Operational transformations requires all operations to pass through a central server for conflict resolution. It's of course much simpler, but also you need a central entity here. CRDTs achieve convergence without any central server. Two nodes can connect directly and merge their states. CRDTs make no assumptions about network topology and are considered the natural successor of operational transformation. So CRDTs shine in decentralized environments without central control, allowing devices to sync via peer-to-peer networks, local Wi-Fi, or any available network path without requiring a central server for conflict resolution. And we covered also CRDTs in our distributed systems lecture. The next article, it's about email protocols. We also covered this in our lecture. It's about JMAP. We did not cover JMAP, but IMAP. So Stalwart announced full implementation of JMAP for calendars, contacts, file storage, and sharing after 4 years of development, becoming the first server to support the complete family of JMAP collaboration protocols. Stalwart is an open source mail and collaboration server written in Rust that supports JMAP, IMAP4, POP3, SMTP, CalDAV, CardDAV, and WebDAV protocols. JMAP, the JSON Meta Application Protocol, is a set of open internet standard protocols for handling email implementation using JSON API over HTTP, developed as an alternative to IMAP and proprietary email APIs. IMAP is already quite old, difficult for developers to learn, and doesn't work well for network-constrained mobile devices. JMAP does not require a persistent connection, making it better for mobile use with intermittent network access, where battery life must be conserved. The traditional protocols have problems. WebDAV and CalDAV and CardDAV, they are XML-based, designed that are verbose. They are sometimes inconsistent and difficult to implement correctly. Information is scattered across HTTP headers, XML payloads, and embedded iCalendar data. creating compatibility challenges. iCalendar and vCard formats contain decades of technical depth with countless properties, many rarely used or obsolete features, making them also error-prone. And JMAP extends beyond email. The new standard includes JMAP for calendars replacing CalDAV, JMAP for contacts replacing CRDTs, JMAP for file storage replacing WebDAV, and JMAP sharing replacing WebDAV ACL, access control lists. JS Calendar and JS Contacts are JSON-based replacements for iCalendar and vCard that strip away accumulated complexity. JMAP allows batching multiple operations in a single request, and you can set different flags on different messages in one action, unlike IMAP, which requires separate operations. Having the same protocol for message, sync, and submission eliminates configuration problems where users can receive but not send emails due to misconfigured protocols. And from a distributed systems perspective, JMAP protocol demonstrates the modernization through stateless design. Unlike IMAP, stateful connections requiring constant synchronization, JMAP uses stateless HTTP requests with batch operations, and this reduces coordination overhead and improves fault tolerance. Clients do not need to maintain persistent connections or handle connection state recovery. The JSON-based approach also simplifies parsing compared to IMAP's custom text protocol, reducing implementation complexity and error rates. And client support is slowly emerging, and Stalwart is now feature complete and targeting a stable release, hopefully sometime soon. And the last article for today, it's about the biggest crypto exchange. It's the following here. US President Donald Trump pardoned Binance co-founder Changpeng Zhao on Wednesday, according to the Wall Street Journal, though no official announcement have been made through the White House website. Binance later confirmed the pardon. Zhao pled guilty in November 2023 to one account of failing to implement an anti-money laundering program at Binance, violating the Bank Secrecy Act, and agreed to step down from his role at Binance. He was sentenced to 4 months in prison in April 2024 and released in September. And the pardon could allow Zhao to return to an executive role at Binance, where he remains the largest shareholder. Under his plea agreement, such a return had been prohibited. Speculation about a pardon grew already in September when Zhao removed the X at Binance tag from his social media profile. And Zhao is not the first crypto figure to receive a pardon from Trump. The president previously pardoned the 3 BitMEX co-founders, including Arthur Hayes, the Silk Road founder Ross Ulbricht, who had been serving 2 life sentences plus 40 years. He was also pardoned by Trump. From a regulatory and governance perspective, this shows the intersection of political influence and cryptocurrency regulation. The pardon effectively nullifies restrictions imposed through the legal process, allowing a convicted individual to potentially resume control of one of the world's largest cryptocurrency exchanges. And this raises questions about enforcement consistency and whether political connections can override financial crime prosecutions. So that's it for this week. See you next week.